Have you ever wondered why certain problems seem impossible to solve with our current computers? Well, it all comes down to the limitations of classical computing. You see, classical computers operate on a binary system. That means they process information in bits, which are either a 0 or a 1. These bits are like the switches that control everything in our computers, from the calculations made by a spreadsheet program to the pixels you see on your screen. But here's the catch. While this binary system has served us well for many decades, it does have its limitations. For starters, classical computers struggle when it comes to processing large amounts of data at once. Think about it. Every additional bit doubles the amount of potential states a computer can process. So, while a computer with 30 bits can handle over 1 billion potential states, the number of states becomes astronomical as we add more bits. And this is where we hit a wall. You see, as we start dealing with complex problems that require numerous variables to be considered simultaneously, classical computers begin to struggle. They simply can't handle the exponential growth in data. Take, for instance, weather forecasting. To accurately predict the weather, you need to consider a myriad of variables, from temperature and humidity to wind speed and atmospheric pressure, and you need to do this for every single point on the globe. Even the most powerful classical computers today would take an impractical amount of time to process all this data. That's not all. Classical computers are also limited by their sequential nature. They process one operation at a time in a linear sequence. So, when faced with a problem that has multiple possible solutions, they have to try each one in turn until they find the right answer. This can be incredibly time-consuming, particularly for problems with a large number of possible solutions. But what if there's a new kind of computer that can overcome these limitations? Enter the world of quantum computing. In the realm of quantum computing, we don't talk about bits, but instead, we talk about qubits. Now, you might be wondering, what's this qubit we're talking about? Well, let's dive in. In classical computing, we have bits. These bits are the smallest unit of data, and they can be either 0 or 1. It's like a switch that can be either on or off. But when we step into the world of quantum computing, things get a bit more quantum. Here we don't have bits, we have qubits. Short for quantum bits, qubits are the fundamental units of quantum information. Unlike classical bits that can be either 0 or 1, qubits can be 0, 1, or a combination of both. This is due to a principle in quantum mechanics known as superposition. Imagine you have a coin. In the classical world, the coin can be either heads or tails, but in the quantum world, the coin can be in a state where it's both heads and tails at the same time. This is what we mean when we say qubits can be in a state of superposition. They can exist in multiple states simultaneously. It's like having a light switch that can be both on and off at the same time. This is a game changer. Why? Because it allows us to process a massive amount of information at once. With classical bits, we process information one bit at a time. But with qubits, because they can be in multiple states at once, we can process information at an exponentially faster rate. This is what gives quantum computers their potential to solve complex problems that are currently beyond the reach of classical computers. So, unlike bits that can be either 0 or 1, qubits can be 0, 1, or both at the same time. This opens up a whole new world of possibilities. We've just scratched the surface of what quantum computing can offer. So, buckle up as we dive deeper into the fascinating world of quantum computing in our next scene. Imagine a computer that can solve complex problems in the blink of an eye. Welcome to the world of quantum computing, a realm where the conventional rules of classical computing are turned upside down. The key to this world is the qubit. Unlike classical bits that exist in a state of 0 or 1, qubits can exist in a superposition of states, being both 0 and 1 at the same time. This means they can hold, process, and share a vast amount of information simultaneously, making quantum computers exponentially more powerful than their classical counterparts. Imagine trying to find your way through a massive maze. A classical computer would navigate the maze like a person, taking one path at a time. If it hits a dead end, it backtracks and tries another path. It's a lengthy and laborious process. In contrast, a quantum computer, with its qubits, would explore all paths at the same time. It's as if it can be at every point in the maze simultaneously, finding the exit in a fraction of the time. The potential of quantum computing is extraordinary. It's like going from a horse-drawn carriage to a supersonic jet in one leap. In cryptography, quantum computers could crack codes thought to be unbreakable, ensuring the highest level of data security. In weather forecasting, They could process vast amounts of data to create far more accurate and timely predictions, potentially saving lives during severe weather events. In drug discovery, they could analyze and simulate molecular structures in a way that's currently beyond our reach, speeding up the development of new treatments and cures. But it's not just about speed. Quantum computing also offers the ability to solve complex problems that are currently intractable for classical computers. They can handle the immense complexity and uncertainty of the real world, from the quantum mechanics of molecules to the vastness of the universe. With quantum computing, we're not just stepping into the future, we're leaping into a new era of problem solving. But the path to a quantum future isn't without its challenges. As we delve deeper into the realm of quantum computing, it becomes clear that this futuristic technology is not without its hurdles. Among the most pressing challenges is maintaining qubit stability. Qubits, unlike bits in classical computers, exist in a state of superposition, meaning they can be both 0 and 1 at the same time. This allows quantum computers to perform multiple calculations simultaneously, a feat unachievable by their classical counterparts. However, this superposition is extremely delicate and can be easily disrupted by environmental factors such as temperature fluctuations or electromagnetic waves. This phenomenon, known as decoherence, is a major obstacle to the practical implementation of quantum computing. Additionally, quantum computers require extremely low temperatures to operate, close to absolute zero, to minimize the risk of decoherence. This need for a cryogenic environment adds another layer of complexity and cost to the development and maintenance of quantum computing systems. Furthermore, quantum computing is an emerging field, and as such, there are gaps in our understanding of quantum mechanics. We are still in the process of developing the theoretical framework and the practical techniques required to fully harness the power of quantum computing. Then there's the question of cost. At present, the development of quantum computers is a highly expensive endeavor, relegated to well-funded research institutions and tech giants. The machines themselves are not only expensive to build, but they also require significant resources for maintenance and operation. Moreover, the scarcity of quantum computing experts adds another dimension to the challenge. There's a pressing need for more skilled professionals who can understand and work with the intricacies of quantum mechanics. Despite these challenges, the world of technology remains undeterred. The potential of quantum computing to revolutionize industries, from cryptography to drug discovery, from climate modeling to artificial intelligence, makes the effort worthwhile. These hurdles are not insurmountable, but rather stepping stones on the path to a quantum future. However, the potential rewards make these challenges worth tackling. Quantum computing represents a paradigm shift in the world of technology. It is a fascinating field that has the potential to revolutionize the way we process information and solve complex problems. Let's take a quick trip down memory lane to revisit the key points we've covered in this exploration of quantum computing. We began by acknowledging the limitations of classical computers. They operate using bits, each one either a 0 or a 1. This binary nature can restrict their ability to handle certain tasks, especially those involving enormous amounts of data or requiring intricate computations. They have served us well, but as we move forward into a data-driven future, their inadequacies are becoming more apparent. Next, we delved into the concept of qubits, the fundamental units of quantum computing. Unlike classical bits, qubits can be in a state of 0, 1, or both simultaneously, thanks to a quantum phenomenon known as superposition. This opens up a vast realm of computational possibilities, allowing quantum computers to process information in ways that are simply beyond the reach of classical machines. We also discussed the immense power of quantum computing. With their ability to perform multiple calculations at once, quantum computers can tackle problems that are currently impossible for classical computers. They hold the promise of accelerating advancements in fields ranging from cryptography to medicine, climate modeling to artificial intelligence. But of course, quantum computing is not without its challenges. The technology is still in its infancy, and there are significant hurdles to overcome. Issues such as qubit stability and error correction are just a few of the obstacles standing in the path of practical quantum computing. As we continue to unravel the mysteries of the quantum world, one thing is clear: the future of computing is not just about bits and bytes. It's about qubits and possibilities.